Good morning students. In today's class we are going to learn problems based on analog Butterworth filter design. So let us have a problem statement. Derive the expression for poles from the squared magnitude response of a Butterworth low pass filter. So how to derive it is, we'll start with the magnitude squared response of your Butterworth filter. This already we have studied in the derivation part. The magnitude squared response of a Butterworth filter, it is given as HAF omega whole square is equal to 1 plus 1 by omega c whole power of 2n. So once you square it, you will be getting it as 1 divided by 1 plus omega square divided by omega c square whole power of n, and name it as equation 1. Then you can replace this s by j omega, and you can assume the magnitudes for HA of s and HA of minus s. Okay, and once you equate it for HA of s and HA of minus s, you can split it as 1 divided by 1 plus s square divided by omega c square whole power of n. Why? Because we know that s is equal to j omega, then omega square is equal to minus s square. So based on that, we have changed the equation 1 as HA of s multiplied with HA of minus s is equal to 1 divided by 1 plus minus s square divided by omega c square whole power of n. So in the next step, we are going to find out the roots of the equation. So once you find the roots of the equation, which is going to provide us the pole location on down. So based on the pole location, we can assume for HA of s, which is lying on the left hand side of the s plate, and the poles which lies on the right hand side, it can be assumed to HA of minus s. And then we can check for the stability of the filter. So for that case, let us simplify this and find out what are the roots of the equation. So for that, you equate that the HA of s directly to 0, and then we can calculate what is the value of s. So here in this expression, take this 1 to the other side, so it becomes minus 1, and even this power of n you raise to power of 1 by 2n, so you'll be getting us minus 1 power of 1 by n. So s square by omega c square is equal to minus 1 power of 1 by n, which is named as equation 2 here. And then as you know, e power of j 2k plus 1 whole power of pi. So this can be expanded as e power of j 2 pi k into e power of j pi. So once you split up this, e power of j pi is 1, and e power of j 2 pi k, it can be calculated as, for any values of n you substitute k is equal to 0, 1, 2, 3, you'll be getting us e power of j 2 pi k 0, 1, 2, 3, you'll be getting us 1. Whereas the value of e power of j pi is cos pi minus plus sin j pi. So cos pi is minus 1, sin will become 0. So e power of j pi, the value is minus 1. So minus 1 into plus 1, it is minus 1 always for any values of k. So in the next step, so let me substitute minus 1 for the value of e power of j 2k plus 1 into pi in the above equation. Okay, so here instead of yes, I am going to replace with e power of j 2 pi k by n here, and then let us simplify it and let us try to calculate what is the value of s. So after solving this particular equation, we are getting the s value as plus or minus j omega c e power of j 2k plus 1 into pi divided by 2n. So we know that e power of j pi by 2 is equal to j, and let us substitute here and simplify. We are getting the s as plus or minus omega c into e power of j 2k plus n plus 1 into pi divided by 2n, where k ranges from 0, 1, 2, 3 up to n minus 1. So this expresses the, so this final equation will tell you what are the number of poles available in the s plane. Whereas if you substitute the different values of k as 0, 1, 2, 3, we'll be able to calculate all the poles for the given Butterworth filter. So actually it is given to derive the expression for the poles. Okay, so that is what we have derived. So the final equation, the sk pole, it is represented as, it can represent each and every pole in terms of S0, S1, S2, and you can substitute the corresponding value of K here, so that you'll be able to determine each and every equation for the location of the poles. So let us go to the next problem statement. So what is given is given G of so the next problem statement is